Hey there. Let's move on in our study of functional groups. This is functional groups number 2. So when we're looking at table R, we're about halfway down. In the previous video, we talked about halides, alcohols, and ethers. In this video, we're going to talk about aldehydes, ketones, organic acids, and the trickiest one of all, esters. The reason I've grouped all of these together is that all of these compounds have a carbon that's double bonded to an O. And that's why we're studying all 4 of them together. All right, our first functional group of the day, aldehydes. This is a hydrocarbon chain that has a C double bonded to an O at one of the ends, or one of the terminal carbons. All right, so we can have a methane that turns into an aldehyde. We remove 2 H's and put on a double bonded O instead. So then this one carbon aldehyde is known as methanal. Al at the end, not Ol like the alcohols we looked at in our other video. All right. It is also possible to have a 2 carbon aldehyde. You pick one of your carbons that's at the end. In this case, they're both at the end. Put on a double bonded O. Make sure you have a proper number of bonds for all of your carbons, all right, and then you can name it ethanal. So we take ethane, drop the E, put an Al on the end instead, ethanal. Our last example here, I took a propane. I located one of the carbons that is at the end. I could have also put one over here instead, but I decided just for fun, really, to put it right over here. And so this propane got turned into an aldehyde, so it's called propanal. None of these need a number because the special group, the functional group, is always on carbon number 1. All right, moving right along, we have ketones. These are somewhat similar because we have a C double bonded to an O. The thing that's different is that this has to happen within the hydrocarbon chain. It cannot be at the end. All right, so the shortest ketone that you can have is 3 carbons in length. I drew one a little bit longer here so that we would have some room to play. All right, and so this 4 carbon chain used to be a butane. I took off a couple of hydrogens, put on an O instead, double bonded O. All right, labeled 1, 2, 3, 4 so that my double bonded O has the lowest number possible. So it's 2-butanone. One is the ending when we have that double bonded O somewhere along the carbon chain. All right, so ketones always end in ONE. This next one used to be, it's a 6 carbon chain, so this used to be hexane. But I took off a couple H's, put on a double bonded O at this 3rd position right here. It could have been at 2, it could have been at 4, could have been at 5. Really, any of those interior carbons would work. But because I put it there, it is 3-hexanone. One at the end because it's a ketone. Okay. Organic acids. Organic acids have more than just the C double bonded to O. It also has an OH group that's attached to that very same carbon. And this has to happen at the end of the hydrocarbon chain. This is because your carbon actually only has one more bond, so it can't really, this group cannot happen in the middle. It doesn't have enough bonds available to link both sides. All right, so we start with the smallest version of an organic acid that's possible, 1 carbon. This 1 carbon has both the double bonded O and the OH group, and so that functional group right there, both of those pieces are attached to the same carbon. So we take methane, we put both of these functional groups on there, all right, and so it becomes methanoic acid. It's pretty clear that this is an organic acid because it says acid right in the name. This next one was a 2 carbon chain. We picked one of our carbons, attached both of the oxygen groups to it, and so this became ethanoic acid. We could also draw the mirror image of that so that the double bonded O and the OH end up over here. Either way, it's still at the end, still ethanoic acid. And just for fun, I drew one slightly longer. This used to be a propane, but I converted it into an acid by adding the double bonded O and the OH group. And so this is known as propanoic acid. And again, this is an example of something that does not need a number, because when the functional group is added, it's always added at the end of the chain, and we always determine that that is carbon 1. All right, we are moving right along. Esters. I hate esters, not gonna lie to you. They are very complicated for me to name. I actually frequently have to look at table R to get a hint as to how to do it. All right, so trickiest functional group to name. It's pretty easy to recognize, but it's kind of difficult to name. So we have a C double bonded to an O, which also has an O on it, but that's gonna happen within a chain. It cannot happen at the end, because this oxygen still needs to bond to something else. All right, so it is possible that we will have some pretty short chains, which are almost named almost like branches, and then this one is just a slightly different size. I picked these two different size chains so you can see how the name goes together. So you find the carbon that is attached only to the oxygen, not both oxygens, and you name that almost like a branch. So it's a 1 carbon branch, and that is known as methyl. We then locate the carbon that's attached to both oxygens, find out how long that chain is. This 2 carbon chain is almost like an ethane, so I started writing ethane, but then I chopped off the E to give it the O8 ending, which is what we use for esters. So this is known as methyl ethanoate, and that's because we have an ethane that's got the 2 O's on it, and this methyl is almost like a branch off of the O. It's kind of named a little bit similar to an ether in that respect. All right, let's take a look at one more. This one is a little bit trickier because I have some more carbons involved. First step, locate the oxygen that is single bonded to the branch. Don't look at the one that has the 2 oxygens on it just yet. This 1, 2, 3 carbon branch off of the O, that's known as propyl. I then locate my carbon that's attached to 2 oxygens, and I see how long that is. That one's almost like an ethane, but we have some special groups on there. So it started out like ethane, I dropped the E and put O8 at the end, all right? And so in both cases we have an ethanoate, and I can identify the ethanoate because that C chain is stuck to both of my oxygens. Okay. Spend a moment, really study how this is going on. It's not necessarily a left versus a right sort of thing. You definitely have to make sure you're finding the carbon with the 2 oxygens versus the carbon that's only attached to 1 oxygen. Take your time with these. All right. We've come to the end of the lesson. Here are 2 different exercises that I want you to do. In the first one, I want you to draw the structure. I would like you to draw me butanone. I would like you to draw me pentanal. I would like you to draw me ethyl propanoate. And I would like you to draw me hexanoic acid. Then on that same sheet of paper, I would like you to draw these 4 structures right here. Now, I may have cheated a little bit. I made the oxygens really kind of obvious, but let's just go with it. This example right here, I've tried to use some black marker to keep them very separate. These things get a little crazy when all of your understood hydrogens are hanging out there. But there are 4 separate examples here, and I would like you to give a name to all 4. All right, do your very best. Bring it in tomorrow. We'll take a look at what you got, and we'll clean up any sort of errors that you may have made. Good luck.